All right, so welcome everyone. Today we're having a special guest from my home field, Jessica Fintzen from University of Cambridge and Duke. And she's going to speak about representations of p-adic groups. Please.
Thank you very much. Thanks for the invitation to join you, at least virtually. First of all, I'd like to encourage everyone who feels comfortable to turn on your camera so that I can actually also see some faces and not just black boxes. I've been told that this is a colloquium style talk and that a lot of grad students are attending. So in particular, grad students are also encouraged to turn on the camera so that I see who I talk to. And I was asked to make it accessible and that people from all the different areas are attending. So I want to talk about representations of p-adic groups, but as a consequence, I don't assume that you know what a p-adic group is or what p-adic numbers are. All right, so let's start with p-adic numbers and p-adic groups. So what is p to begin with? So p should be a prime number, like 2, 3, 5, 7, 11, 13, whichever prime number you want. And then we want to talk about the p-adic numbers. And in order to define them, we start with the p-adic absolute value, which is the following. If you take an integer, you can write it as p to the power of s times r, where r is coprime to p. And then you'd say that the p-adic absolute value is 1 over p to the s. So in other words, the more often the number is divisible by p, the smaller is the p-adic absolute value. So it measures how often the number is divisible by p. And then you can define the p-adic integers to just be the completion of the regular integers with respect to this absolute value. And so what happens if you do this? It means that powers of p become very small. So that means the p-adic integer is of this following form. It's a power series essentially in p, where these coefficients are some integers between 0 and p minus 1, because the larger the power, the smaller the absolute value. So this power series here converges within the p-adic integers. And so that's how you can think of p-adic integers. And then the p-adic numbers, they are just the fraction field of these p-adic integers. Or another way to obtain them is to start with the rational numbers and complete them with respect to the p-adic absolute value. So that at first glance sounds maybe a bit odd, but let's try to see actually how do they look like. So what are the p-adic integers? How do they look like? So I said these are power series where you have these exponents of 3 where the exponent increases, and the coefficients are 0, 1, or 2. So if you just look at the first digit, so that could be 0, 1, or 2, and the distance between these two is 1, because the difference is 1 minus 0 is 1, which is not divisible by 3, so the absolute value is 1. And if we add now a second digit to it, so if we, for example, look at 1, 0, so that's 1. 1 plus 0 times 3 is 1. Or at 1, 1, so that's 1 plus 3, so that's 4. The difference between 4 and 1 is 3, which is 1 divisible by 3, so the p-adic distance is 1/3. So that means by adding the second digit, we get these smaller triangles. Inside each triangle, the distance between two members is 1/3, and each of these elements in the triangle has distance 1 to any member in this triangle. And now I think you can understand the pattern. If you keep going, you just add more and more smaller and smaller triangles. And so if you keep going, you get a fractal. So the p-adic integers, they are fractal. And that's somehow how to think of them. That's how they look like. So very different from the integers.
Jessica, can you repeat on the definition of p-adic numbers?
Could you repeat?
P-adic integers, excuse me, forgive me, p-adic integers. The definition, can you repeat the definition?
Sure. So the definition is that you start with the integers, and then you complete the integers with respect to the absolute value, the p-adic absolute value, which just means, in other words, you just look at all these power series. And if you stop the power series after the third term, you get an integer, but you can keep going and this power series will converge. So in particular, it contains all the regular integers, but it also contains these infinite power series.
Okay.
Good question. Further questions at this point? Okay, and so as I said, since you have these power series, this ends up looking like these fractals. Like this number here in the corner is always 0. 0 plus 0 plus 0. I mean, the digits here correspond to the coefficient. So this is 0, this is 1, but you can also get all kinds of other power series that are not integers necessarily anymore. And so I like to contrast it with the real numbers, because I said one way to obtain the p-adic numbers is to either take the fraction field of the p-adic integers or to just start with the rational numbers and complete them. So these are the p-adic numbers. And this might sound familiar with you if you think of the real numbers, because how do we obtain the real numbers? We obtain them by starting with the rational numbers and then completing them with the regular absolute value. That's one way to construct the real numbers. So in some sense, for the real numbers, one way to think of it is that you look at decimal numbers, and after the point, you can go to infinity, while for the p-adic numbers, somehow you go to infinity in the other direction in front of the decimal point. But so even though the constructions are similar, it's both a completion of the rational numbers, they look very different. The real numbers, that's this line here, where the rational, the p-adic numbers, that's this fractal here. So in particular, the real numbers that are connected, while the p-adic numbers, they are totally disconnected. So the topology is very different. And that's why the p-adic numbers, p-adic groups behave so different from the real numbers and real groups. So one important difference between the two is that if we look at the real numbers, there's only one compact subgroup and addition. Because if, for example, say the number 2 is inside your compact subgroup, then the number 4 has to be in, the number 6, 8, and so on has to be in. So it's never compact. On the other hand, for these p-adic numbers, there are infinitely many compact subgroups and addition. Because, for example, the p-adic numbers itself, so the p-adic integers themselves inside the p-adic numbers, they are a compact subgroup, because I mean that's the factor we drawn here, so it's something compact. Or if you look at p times vp, which corresponds to all these smaller triangles, or p squared times vp, or p to the 15 times vp, all these are compact open subgroups. So there are a lot of compact open subgroups, and they even form a basis of neighborhood. And that's what's making these p-adic numbers so different and so interesting. And so I said I want to talk about p-adic groups. So let me tell you what they are. So you might remember what Lie groups are, real Lie groups. For example, GLN over the real number, SLN over the real number, or SON, those matrices that preserve an inner product, or SP2N, those matrices that preserve a symplectic form. And now if I want to talk about p-adic groups, I just do the same, but instead of the real numbers, I plug the p-adic numbers in it. So I look at all the invertible matrices with coefficients in the p-adic numbers, for those that have determined 1, or those that preserve an inner product, or those that preserve a symplectic form. And you might remember for real Lie groups that there are also these exceptional ones, these E6, E7, E8, G2, and you can construct something similar for p-adic groups. But I think the main way of thinking about them is just that you take these real Lie groups you're familiar with and plug in the p-adic numbers. So just matrix groups over the p-adic numbers. All right, so these are the p-adic groups. I want to add one more detail to it. So if we look at the p-adic numbers, so I said the p-adic integers are these power series in P. If we look at the p-adic numbers, it means we take the fraction field, or we start with Q. And another way to understand this is to allow negative exponents of P, but only finitely many. So you start at P to the minus n, and then go up all the way to infinity. So that's another way to think of them. And so a question I commonly get by people working in PDEs is, what is the characteristic of the p-adic numbers? And the characteristic is 0 because the prime number p itself is non-zero. P itself lies here. It's a p-adic number that is non-zero, and all the other prime numbers can be written as the sum of a0 plus a1 times p and so on. That is non-zero. So none of the prime numbers is 0 in this field. So it's a field of characteristic 0. But the question is a very, very good question, because there's this tightly related field, which are the Laurent series over a finite field with p elements. So this means we look at Laurent series, which means we have some dummy variable, some variable t. We allow finitely many negative exponents, and we can go to infinity for the positive exponents. So it's again power series, but with negative exponents allowed. So we call this Laurent series. And the coefficients are coefficients in the finite field with p element. And you see already the similarity. It looks almost the same, except that here p is the variable of our Laurent series, and here we have an actual variable t. And so the main difference is that this field now has characteristic p, because P is an element of this finite field with P elements, which corresponds to A0, and P is equal to 0 in a field with P elements. And these fields are closely related. They are very similar. And if the p-adic numbers are new to you and you're maybe more used to Laurent series, maybe over the complex numbers, just think of Laurent series, but now plugging in the finite field with P elements. Or if you're familiar more with p-adic numbers, think of the p-adic numbers. Because everything I'm going to tell you about should basically hold for all these groups. So when I talk about p-adic groups, I not only want to think of groups over QP, but I also allow you to plug in these Laurent series over finite field with P elements. So you can choose which one to think. And I call both p-adic groups. All right, so that's the idea of what p-adic groups are. Now I would like to move forward to the representations of these groups. So let's fix some notation. So G is now from now on a p-adic group. So one of these groups you have seen on the previous slide. If this is new to you, just fix one of these groups in your mind and think of it the whole time. If you're familiar with reductive groups, just think of the most complicated reductive group you can think of. And so I want to study representations. So recall that a representation of a group is just the group homomorphism from this group into the space of automorphisms of a vector space. And this vector space could be either a complex vector space, or it could be a vector space over FL bar, which I then call a mod L representation, as long as L is different from the prime P, the P of the p-adic. And this vector space V is usually an infinite dimensional vector space. So these are huge representations. And what we want to do is we want to construct all these representations. But I put some small words in here because I said this is usually infinite dimension and we want to get something that's reasonable to work with. So I put two words in here. Irreducible means we look at the building blocks, which are those representations that contain precisely two sub-representations, the trivial one and the representation itself. And smooth means that I told you we work with p-adic groups, which are groups over these p-adic numbers. And we've seen that the p-adic numbers have a topology. We saw this fractal. And so from the topology of the p-adic numbers, we obtain the topology of the p-adic group. And smooth means that something that takes the topology into account. More precisely, it means that if we take a vector in this vector space on which we act, on which the group gets sent to automorphism of the vector space, then we want that this vector, each vector, should be fixed by an open subgroup. So that means a rather large subgroup fixes each vector. So even though our representation is infinite dimensional, a large part of the group, an open subgroup, fixes each vector. So for each vector, we find some open subgroup that fixes it. And this somehow gives us some nice way to deal with these representations. This is a nice subcategory of the representation that you can actually work with. If you don't impose that, it's just getting crazy. And so that is the big goal for a lot of mathematicians in representation theory. That's what we really want to do. We want to construct all of them. Now you might wonder, why do we want to do this? So let me give you some motivation. So first of all, it's helpful to know how to construct this representation if you study the representation theory of these groups. I guess that's not so surprising because if you want to study the representations, knowing how they look like is really helpful. For example, if you want to study how does a representation behave, then you restrict it to a subgroup. For this, it really helps to be able to write down the representations explicitly. Or if you want to study the so-called Howard correspondence between representations of different groups, you want to understand, or you want to know how to write down these representations to say, this representation gets sent to that representation. Or if you want to write down the Harshanda characters, a character that really determines the representation, similar to characters of finite groups, you actually need to know first how to get a hand on of these representations, how to write them. But there are also applications far beyond the representation theory. One application that's rather unsurprising is towards an explicit local Langlands correspondence. The idea of the local Langlands correspondence is that to each representation of a p-adic group, you are able to attach a Galois representation. And if you want to do this explicitly, you really want to know how to write down these representations in order to attach something explicitly on the other side of the local Langlands correspondence, to attach a Galois representation on L parameter. There are also applications to the global words, to automorphic forms. Automorphic forms are a generalization of modular forms, and they played an important role for Hamas last theme and things like that. And so, for example, one application is a joint work of myself with Sogu Shin, which we posted on the archive last year, where we produce congruences between arbitrary automorphic forms and particularly nice automorphic forms. And that in turn then had applications to the global Langlands correspondence. And our approach really heavily relies on just understanding the representations of these p-adic groups. And there are also more funny applications, maybe more exotic or surprising applications, for example, to the mirror symmetry conjecture. And I put the ... here because there are many more applications, and maybe you'll encounter some yourself. All right, so that's just an idea of why you might be interested in these things. And what I want to do next is to tell you actually what do we know and what don't we know, and how do these representations look like. Are there any questions at this point? All right. So let me repeat, our goal is to construct all the representations. And how do we do this? We know that there are certain building blocks, and these are called supercuspal representations. Or if you work model, they are called cuspal representations. A lot of people are scared of it. I don't actually know why, maybe because it contains the word super in it or so. But supercuspal representations really just means building blocks. If you ever hear supercuspal representation, just think of, oh, that's just the building block. And the precise mathematical idea is that every other representation arises in the parabolic induction of a supercuspal representation. And parabolic induction is something one can write down and can then study. And the supercuspal ones are those that do not arise in a proper parabolic induction. So these are those that we need to construct in a different way. And that's why they are really mysterious, because we can't just write down a parabolic induction. And that's why it took mathematicians a long time to be able to even write them down. And so I want to tell you what we know, what we can write down. So it started with work of Howe and Moy in the 70s, 20 years ago. And they started with the work, they started to study the group GLN, just the invertible matrices, because I think that's the natural thing to start with. And then around 25 or 30 years ago now, Bushnell and Kutzko finished it and showed how to construct all the supercuspal representations for the general linear group. And again, there are a lot of dots here, or actually only 3, but there should be more dots because a lot of people worked on this in the meantime and proved a lot of intermediate results. And I should also say that shortly afterwards, Marie France observed that the same works also model. So I write the model things always in blue. Model things might be interested if you think of the local Langlands and families or things like that. If this is a completely new topic to you, just focus on the complex representations and everything is fine.
So did she had to use Bushnell-Kutzko, or it's like a parallel approach?
Yeah, no. So what she shows is that the same, if you use basically the same construction but substitute complex numbers by FL bar, then it works. It's a bit simplified, but it's really the analogous construction. The only difficulty is that the proofs are more difficult in the model setting because there's just complications. So for example, if you think of representations of finite groups, if you look at complex representation of finite groups, you know that they are semi-simple. So all decomposed into direct sum of irreducibles. But this is no longer the case for model representations. They might be not, you have non-trivial extensions in that case. So there's a difference between irreducible and indecomposable. And this implies that there are a lot of complications in the model setting, but the construction is essentially the same. Yeah. Good question. Further questions? All right, and then the next step was that people looked at classical groups. So what are classical groups? These are just fixed points of involutions inside GLN. So that's like unitary groups, symplectic group, orthogonal groups. And the way Sean Stevens dealt with it, so Sean Stevens showed around 10 years, 12, 13 years ago now, that he obtained how to obtain all the supercuspal representation in that setting. And he basically used also the GLN story and made sure that everything is invariant and not in involution. it's not that easy. It's more difficult. You have to work much harder for classical groups, but he essentially uses the same languages and relies on the construction of Bushnell and Fintzen. And not so long ago, Korinchuk and Stevens showed that the same works model. Again, it's the same construction essentially. But the proof is a bit more difficult. And also inner forms of GLN were treated by Chiari and Stevens roughly around the same time. So what are inner forms? Inner forms just means GLN over some division algebra. So for example, it means you just take your favorite division algebra and take the units inside the division algebra. And so all these cases basically rely on how it worked for GLN, all use the story for GLN, the language for GLN. And what I'm really interested in is to go beyond that, to do something for all the p-adic groups that are out there, also the exceptional and crazy ones, all at the same time. And there, the story started much later. So let me tell you what you know in that setting. So in that setting, it started with the work of Moy and Prasad in the mid of the 90s, and they defined the notion of a depth. The depth can be either 0 or a positive real number, and it measures somehow how complicated the representation is. So this is an invariant that they attach to each representation. And I want to draw a picture now where I draw in this direction the prime number p, because some results depend on what the prime number p is. And so what Moy and Prasad did is they showed how to obtain all the depth 0 representations. So all these representations appear. And I should say that Morris did the same roughly around the same time, but using a slightly different approach. So he has some independent proof of the same result, essentially. And the idea is that depth 0 representations are roughly the same as representations of finite groups of B time. And that's how you see there's this connection to representations of finite groups. But now we are interested in also going beyond the depth 0 case. And the first general construction was provided by Jeff Adler in 1998 in his PhD thesis. And then 3 years later, JKU generalized this construction vastly. So I've drawn all these dots here, which represent representations that they constructed, and they now have positive depths. And so JKU's construction is actually the construction that everyone uses nowadays, essentially. Like when I say that we want to know how to write down these representations, to study the restriction to subgroups, to study the Howell correspondence, to study the Harshanda characters, to write down a local Langlands correspondence. For all these things, people usually use JKU's construction because this is the most general construction that's known today. So if this construction is so widely used, we want to know what can we get out of this construction. It's natural to us all stochastic representations of that form. And so in 2007, Julie Kim provided a big breakthrough, essentially. She showed that all the representations arise from JKU, all the supercuspidal representations arise from JKU's construction if the prime number p is very large. So if we are in this region here, and if the field is QP. So if we work with the p-adic numbers, not with the Laurent series over a finite field with p elements, but with QP. In this setting, we have exhaustion here, so everything arises from use construction. So everything that we prove for use construction works for all the supercustom representations. So we obtain general results. So that's really useful because now if we want to prove something for all representations, we just work with use construction. But so you might wonder,
does this have to use the local Langlands or
no, this has nothing, no. So this result is just representation theoretic. Local Langlands comes afterwards. If you want to write down local Langlands correspondence, then if you want to do it explicitly, you use construction to do so. But this use construction and the exhaustion comes first. That's just representation theoretic. Good question. So the next question would be, okay, for very large primes and for QP, we know what to do, but what happens for small primes? So in 2014, Mark Wieder and JKU, they gave some construction of other representations. They constructed these representations that are circled here by yellow dots, and they called them epilogical representations. So why did they call them that? Like that, such a weird word. It's because the representation they construct have smallest positive depth, so they have very small depth. And why do you use epilogic? It's because of oceanography. Mark Wieder told me that he thinks of a representation as a fish that swims in an ocean. So one of these weird creatures, and we have to find all of them, understand them. And the the representations that they constructed are lying in the epipelagic zone, in the upper zone of the ocean. It's a zone that can be reached by sunlight. That's why they use the word epipelagic. And so the way they did it is to say, okay, we assume there exists a nice input, which they call a stable vector in the multiple filtration. Then they perform a construction, and the output are these epipelagic representations. But they could also show that.
Did someone try to define mesopelagic, or the people stopped with this analogy?
So there are some, I've seen someone talking about mesopelagic representations, but I do object. I don't really like the way some people use it. I mean, yeah.
There are disagreements on the definition. Okay.
Yeah, I mean, they just thought, oh, that's a nice representation. That's not epipelagic, so call it mesopelagic. But I mean, one big difference is there are only, I don't know, 5 zones here, while for depths it goes to infinity. And so you run very soon out of these zones. And also, yeah, so some people use it, but I'm already not so happy about the precise definition of epipelagic, because epipelagic representations can get as complicated as you like. So there are more epipelagic representations than the one that arise from Yida and Yu. Yida and Yu only produced some of them, but if you look at the definition, there are others that are more complicated. So, well, I think it's a nice terminology, but I think we have to be a bit careful with how to move on. Yeah, but people do start talking about mesopelagic for different things. Further questions about math or oceanography?
Thanks.
So yeah, so the way what I just said is that Yida and Yu, they took a certain input, and the output are epipelagic representations. But maybe I should say, I really like the way of calling them epipelagic. On the other hand, I think that's a smart move rather than called. I mean, it's much more creative than just random names people make up, which are usually good or bad or things like that. So I said again, they take an input, the output are nice representations, but they only showed the input exists for large primes. And so what I did recently, partially in a joint work with Stefano, for the special cases, that we showed actually the input exists for small primes as well when the input exists for large primes. And that means we get a lot of new representations down here for small primes p that were not constructed earlier by JKU. So that means there's actually much more work we have to do. And you might wonder, are there maybe representations that have higher depths because there's a lot of space here? And the answer is yes, but I can't tell you the details because I'm still working on it. And that's really a big project that will still take quite some time to work. Instead, what I like to tell you about is this different zone here. The zone where the prime p is just large and not very large, because there are a lot of dots here. So the question is, in which region do we actually get everything from used construction? And this region turns to be much larger. We only have to assume p is large, not very large. And moreover, you saw that Julie Kim assumes that the field is QP, and I want to remove this assumption as well. I also want to work with the whole series over finite field, because I told you at the beginning, these two fields, they are so similar. Why should we just work with one and not with the other? I mean, there's a reason why Julie Kim only worked with one, not the other, but that reason doesn't have to be there. That reason was just for her purpose was needed, but the result holds in full generality. So that's the theory. Suppose the prime p is large. And what do I mean by large? Maybe I'll say it in a second. Suppose p is large, then use construction provides all supercustom representation. And so large means that p doesn't divide the order of the Weyl group. What is the Weyl group? So for GLN, the Weyl group is Sn, this symmetric group on n letters. So the order is n factorial, so the prime has to be larger than n. So that's this first case here. For other classical groups, in the worst case, you see the order is 2 to something times n factorial. So in worst case, we exclude all the primes up to n. So we don't actually exclude that many primes, even though this order is huge. And for these exceptional groups, in worst case, we exclude the primes 2, 3, 5, and 7. So we actually don't exclude that many primes. And under this assumption, everything arises from used construction, so we can just work with used construction and prove all kinds of nice theorems.
So what used to be very large? How large?
Oh, that's a very good question. Very large. So I need to add one more detail here for the number theories. So instead of just working with the p-adic numbers, you can work with finite extensions of the p-adic numbers. So take your favorite finite extension and look at the ramification index. Let's call this ramification index E. Then if you look at the group GLN over this field F of ramification index E, then the prime P has to be larger than, first of all, N, like the assumption I did have, and also larger than E, the absolute ramification index. Or most likely, the assumption is rather that it has to be larger than N times E, something like the product of the two. But it's rather difficult to write down. But the main message is that it actually depends on the field you work with, and this assumption might be really a huge assumption. So if you work with a highly ramified field, then the prime P has to be very large to be allowed. Good question. Further questions on that one?
Those groups, maybe you talked about the construction of our presentation. Was the representation okay? It was for the p-adic group. I'm sorry, I understood what I asked. Thank you.
So I'm not sure I understood the question.
I was just like, I understood what I wanted to ask, so it's fine.
Ah, okay, so that's great. So everyone is happy. I'll also show you how a representation looks like in a bit so that you have an example to take away from that. But first I want to mention that the same construction works also in Mod L. So you can construct all classical representation using the same analogous construction. We just essentially replace the complex numbers by FL bar. And I like to also remark that this is the best we can hope for essentially. So I expect this condition to be optimal. And for small points, you really have to work harder. You need the new construction. New construction is not enough. I put a little star here because I don't really want to go into the details of what precisely I mean by optimal, but the main message is you have to work harder if you want to get to smaller points. All right. So that's basically the story, how it looked like. But then, well, there was a small problem, or rather a big problem, huge problem, that a colleague of mine, Lawrence Spice, realized that actually use proof doesn't work. What do I mean by this? JKU provided a construction of representation and then proved that this construction provides us with supercustom representations. And everyone else went away and said, yeah, we have supercustom representations, let's work with them. And his proof doesn't work, or more precisely, his proof relies on a typo in a reference. It's a paper by Jaredell from the 70s. I think the time when you handwrote your papers, gave it to a secretary who typed it for you. And in this statement that JKU uses, a +-1 is missing. In the statement of the theorem, not the proof, in the statement of the theorem, a +-1 dropped out, it's just missing. And the problem is, if you put this back into the statement and then plug this into JKU's proof, the proof doesn't work, it breaks down. No way it works. Maybe you should even say, not only does the proof not work, there exists a counterexample to the key ingredient in his proof to this proposition 14.1 and theorem 14.2. It doesn't really matter what this is for you. But what matters is that JKU says the main ingredient in the proof are these theorems, these propositions, and they are just false. They are counterexamples. So, well, that was a scary moment because we weren't sure, like, does everything break down? Are these representations that we assume to be supercustom really supercustom? And, well, I guess there are two reasons why I could talk about it, either to ask you to fix it or to tell you that it's already fixed, and it's the latter. So we don't have to worry. Use construction actually does work. So instead of using his proposition 14.1 and theorem 14.2, I use his first half of his proof and then substitute the second half by something different that doesn't rely on this typo in the reference. So we can breathe again, everything works. The literature is still fine.
So was there like a new insight in this fix? I mean, there's some new, I don't know,
This is a very good question. So you mean not
Like,
just the
what
way I
did
think?
you learn that wasn't there in the original paper?
I mean, of course, the arguments for the second half are different, but I think a better answer to your question is to tell you the following. So what I did was just to write a much shorter proof so everything is fixed and we don't have to worry. But on the other hand, these propositions, they are still very important. And another way to fix this is the following. That's joint work with Tasha Kaleta and Lawrence Spice. That what we do is we twist JKU's construction. So basically I said a plus minus one was missing in one of the references. And what we do is we twist JKU's construction by a plus minus one such that they cancel each other out. And then the proof works again. So then we can use the old 30 pages of JKU. And instead of substituting 15 pages of his by 3 pages of mine, we add another 15 pages or 30 pages to it. To prove that actually this twist exists and does what we want it to do. And so now you might wonder, why do we care? Because we have already this fixed. But the why do we care is to answer Max's question. The why do we care is because we think it provides us with a lot of new insights. And maybe that's what you were asking for. Because we think that this twisted construction might be a much more natural construction. Because a lot of times in the literature, people had to put in some additional twist that didn't really seem like belonging. So for example, to write down an explicit local Langlands correspondence, people often put in a twist. And it seemed like not natural to put it in. And so basically what we think is that maybe our twisted representation is the more natural one that doesn't require all these twists. And moreover, a lot of obstructions go away. So Lawrence Spice wanted to calculate a character formula, but he needed to twist the representation for obstructions to go away. So our twist provides the solution. Tasha Kaleta wanted to write down a local Langlands correspondence for non-singular representation, so a large class of representation. But in order to do so, he needed to know that such a twist of JKU's construction exists. So our twist makes this obstruction go away.
So the twist depends on some extra information that you put in?
So the twist, yes and no. So it's somehow, I don't really like the word canonical, but my co-authors like to call it canonical. So the way JKU's construction works is that you take a certain input and then perform a construction. And our character just takes this input, and out of this comes a plus minus one character. So it depends on the input for JKU's construction, what this plus minus one is.
So in the end, you have like the right way, the right twist.
Correct. Yeah. So that's the idea. That we twist it depending on the data for JKU, we twist it, multiply basically the inducing data by plus minus an appropriate quadratic character. So character valued with plus minus one. That makes everything else in the literature work somehow much smoother. And in particular, it fixes these broken parts of JKU as well.
Okay, thanks.
You're welcome. Further questions? All right, then this was like the broad overview. What I would like to do next is I want to show you an explicit example. I first want to show you more general how we construct it, and then show you an explicit example to give you some feeling for how these representations look like, so that you go away and don't just think, oh, there's a dot, but that you have seen one. So in general, there's a folklore conjecture that all these representations arise in a two-step process. The first step is to construct a representation of a compact subgroup. So for example, of SLN ZP inside SLN of QP. And then the second step is that you build a representation of the whole group from this representation rho K of the compact subgroup. And this second step is called compact induction. So that's something well known, and I will recall it in a bit. So in order to do this, we need to, or maybe let's go back. In order to do this, I said we have these we need this compact open subgroups. So I need to talk about compact open subgroup, and they arise from filtrations. Filtrations of p-adic groups by compact open subgroup. And maybe to begin with, one motivation for why one would like to look at filtrations is the following. So I said our representation is smooth, which means that every vector is fixed by some open subgroup. But we don't know what this open subgroup is. It could be huge, or it could be very, very tiny. And so the idea is that we define a filtration, so-called multi-sub filtration, consisting of compact open subgroups that are getting smaller and smaller and smaller and smaller. And then one of these subgroups has to fix our vector. And that's also how the depth is defined. It's defined on how far do we have to go down in this filtration until we can fix it. Okay, so this is still the 10 radius. So let's go into the filtration. How do they look like? So I said a p-adic integer, you can think of it as this power series where these coefficients are between 0 and p minus 1. So there's some natural filtration. So we have the p-adic integers. Inside there we have p times the p-adic integer, the smaller triangle, which corresponds to just this a0 being 0. So we just start with p times something. Inside there we have p squared, so this even smaller triangle, which corresponds to the first two coefficients being 0, and so on. So we get smaller and smaller triangles, smaller and smaller compact open subgroups under addition. And now the idea is just to do the same for the p-adic groups. How can we do this? Let's look at the case of SH. We can have the compact open subgroup consisting of all the matrices that's determinant one whose entries are inside the p-adic integers. Inside there, we can take all these matrices that are congruent to 1 mod 3. So the diagonal of the form 1 plus 3 times dp. So the first coefficient is a 1, while the off diagonal, the first coefficient is a 0. And then we can look at those that are congruent to the identity mod 3 squared, 3 cubed, and so on. So that way we define a filtration. This is a congruence filtration. This is the one people usually come up with if you were asked for one, which is also a very common filtration in number theory. But the idea of Moyen-Passat is to realize this a bit differently. And so the way to do this is to think of a Brech-Dietz building. So I think before the talk started, we talked about buildings for other reasons. This is a mathematical building. So what is a mathematical building? Mathematical building is a lot of real vector spaces that are glued together. In this case, it's a lot of lines glued together. So here it's one line, here's another line, and the dots indicate even more lines. So there are a lot of lines glued together. And the group acts on this. And Brian and Tietz define it in such a way that this encodes compact open subgroups. Because if you look at a point inside the building, you can look at what is the stabilizer of that point. And the stabilizer of that point, in this case, is this first compact open subgroup here. And if you think about it, if you fix a point, you get a compact open subgroup. Now you want to get a smaller compact open subgroup. How can you do this? You can do this by just fixing more. And so that's basically how this filtration is defined, roughly. The first filtration subgroup, zeroth filtration subgroup, is just fixing, so it's the point y0, and it fixes the ball of radius 0 around it, just the point. And the next one is, again, the point y0, but we fix also ball of radius 1 around it, so everything that has distance 1 from it gets fixed. So that's the next filtration subgroup. And then we can keep going. Now we can fix everything that has radius 2, everything in a ball of radius 2, so that has distance most 2. And then we get the next filtration subgroup. And that's how we can keep going. I'm flying slightly here because the precise definition of the Moyen-Passat filtration is a bit different, but the essential idea is this. So it's just a defined index that I'm lying, but that's really the way to think of it. Just think of fixing larger and larger balls. And that also indicates that we can do this with different points. So if we do this with y1, let me just move things down to have more space. This was the filtration we had before for y0. If we do it for y1, the first group we start with is slightly smaller. Here's this 3 already in the upper right corner. So here the a0, the first coefficient is 0. And so now something interesting happens. Because this is already a smaller subgroup, somehow we go down in 2 steps. In the first step, at depth 1/2, we change the diagonal. And at the second step, we change the off diagonal. Then we change again the diagonal. And then we change the off diagonal. So change just means we make it slightly smaller. We impose an additional condition. And this is essentially how all the Moyen-Passat filtrations work. We always have the diagonal that we change at certain steps, and then we have the off diagonal that change at different steps. And the building tells us when do these changes occur. And I should say I've written down just some of these filtration subgroups for 0, 1/2, 1, and so on, but they actually exist for all real numbers, but all the groups in between here are the same as the one at 1/2. So that's why I didn't write down all of them. And the same here. The group here at 1/2 would be the same as the group at depth 1. And so that means we get this filtration of our group by compact open subgroup. And this filtration plays a really important role in representation theory because it allows us to construct representations, to understand representations, to study them, to define the depths, and all these things. And it has a lot of nice properties. The quotients are really nice, and I could give a whole talk just about this filtration. But here I just want to give you some idea of how it looks like. And next, I would like to show you how we get representations out of this. So that's the last section. Let's move to representation. So here we go. What do we need? We need a compact open subgroup, okay, and we need a representation of it. So let's take the example of SA2, QP, and let's take this compact open subgroup here. We have seen this before. This was the filtration subgroup. This was the filtration subgroup at depth 1/2 at depth at the point y1, and we also take the center into account. And now we want to construct a representation of it. And so I want to make it easy and want to construct a one-dimensional representation. So map from this compact open subgroup to GL1 of the complex numbers, which is just the invertible elements in C. So in other words, I want to construct a character, a map from K to C star, the group homomorphism. So how can we do this? So the plus minus 1, we just send to 1. Just why not? That makes it easy and we can forget about it. So the tricky part is really, what do we do with this compact open subgroup here? And as I said, this is this filtration subgroup that we have seen before, this filtration subgroup at depth 1/2 at this point y1. And so how can we possibly get some finite dimensional representation, a character out of it? The first step is we just mod out the next filtration subgroup. And these filtration subgroups, I didn't say, they are all normal inside each other. And the quotients are particularly nice. So this quotient here, what is it? It's only the off diagonal that changes. So this corresponds to just a finite field with 3 elements on the off diagonal, because the difference between Z3 and 3 times Z3 is just this coefficient A0, which can be anything in F3. It can be 0, 1, or 2. And so now we are left with this finite group. So it's a finite group under addition. And so we can just take a matrix A and B and send it to the sum A plus B. So that's an element of our finite field with 3 elements, 0, 1, and 2. How do we get a complex number out of it? We just send it to the third roots of unity and raise it to the power A plus B. And so that way we get now a representation, a map from this compact open subgroup to C. So it's just this whole combination gives us the desired map. So that's good. We have a compact open subgroup and a representation out of it. And now the next step is to do the compact induction. That's the second step. And what's the compact induction? It means we look at all the functions from our group G, our p-adic group, this SA2, Q3, to the complex numbers, such that f of kg, where k is an element of capital K, is the same as this representation, this character applied to k times f of g. So the function transforms on the right via this representation. And we want it, so that's done with induction, but compact induction also means we want this function to be compactly supported. Remember, our group has a topology, so it makes sense to talk about compact. And this is a huge space. It's roughly the space of functions on G mod K, which is infinite. So it's an infinite dimensional vector space, and we can act on it via right translation. And that's how we obtain representation. And the difficult part then is to prove that this is a supercustom representation. And this representation is even more special. It's even an epilogical representation, one of those constructed by Reader and Newey. And it's even more special than that. It's even a simple supercustom representation, which was constructed by Gross and Reader beforehand. I've mentioned that before. They constructed representation before the epilogical. And, well, that's an example of how representations look like. And the general construction of JKU is along the same lines, but maybe it's better if I wait to the next slide to say more. But the main idea is that we need some representation of a compact open subgroup like this character, and then we compactly induce it. Oh wait, are there any questions on this? Okay, so then I would like to use the remaining minutes to give you an idea of, so this is how a representation looks like. And I showed that all representation arise from used construction. So I want to give you an idea of how one can possibly go the other way around and prove that everything is of such a nice form. So I just made the slide a bit smaller to fit a bit more on it. So this is what we just did, construct these representations. So what we did is we started with a group, SA2. We started with a point in the building. We started with the depth and the character. Broker here, this character that I constructed for you down here. And then we perform the construction by JKU, or in this case, it's even reader use construction. And the output is that we obtain this supercustom representation, which is this compact induction here down here. So this compact subgroup from where we induced is just the filtration subgroup at depth 1/2 and ±1. All right, so that's what we did. And now I want to tell you how do we go the other way around. So I have to remove the last slide to have more space. How do we go the other way around? So if we start with this representation, the compact open subgroup, we somehow need to figure out what the input was. So, or rather, if we just start with this representation, we'll encounter the compact open subgroup as well. How do we get the input from it? So first of all, how do we recover this real number? This real number R is just the smallest non-negative real number such that the representation pi has a non-trivial fixed vector under GY1 R plus. What is this R plus? It just means the next filtration subgroup. So in our case, this would be GY1 1. Because we saw, let me go a slide back, we saw that this filtration subgroup acts trivially, so they are fixed vector under this subgroup. And so we just go down our filtration of compact open subgroups until we find a subgroup that has a fixed vector. And once we have the subgroup, now we know that actually that means we have our vector space. So say that's the representation pi x on a vector space V. That's our representation. And now we know that if we look at the fixed vector under this R plus, or R plus is equal to 1 in that case, we know that this is non-trivial. And so that means that on this, we have the group GY1 R mod GY1 R plus acting because R plus acts trivially. And so then in this vector, so this is actually an abelian group, at least if R is greater than 0. So this is, let me recall on the previous slide, this is what previously was this abelian group here. This was the quotient of GY1 half mod GY1. And so this acts now on the fixed points. And if an abelian group acts on some vector space, this representation decomposes into characters. So that means it acts via some character. And this character, one of these characters is this bouquet. Or in other words, it's the bouquet that we constructed before this bouquet. So that's how we can go the other way around. That's how we can construct this input from the output by just looking first, how far do we have to go down to we have fixed vectors? And then we study the space of fixed vectors and see how the next level acts on it. And that's how we construct it.
So in this other direction, you first don't assume that rho k is a character, right? Because you take...
So this is in the other... And what, sorry, can you repeat that?
What is rho k? It's not one-dimensional?
So in this specific example, it's one-dimensional. But so what happens in general, it will be much more complicated.
That's an example, okay.
In this specific, yeah, so I'm cheating here because I say how to recover the input from the output. And of course, not everything arises from year-to-year construction. So this is very specific to this specific case. I just wanted to give it to you as a baby example because I want to show you next how use construction works. And there it's much more complicated. So let me maybe move to that and then you'll see how things work. But the idea is basically in this easy setting, if we just look at the depths and look at the fixed vectors, it turns out that we actually recover everything because the way we constructed the representation was to just induce from this depth 1/2 filtration subgroup. So we actually obtain all the information. But you're right, this is very specific to the specific example. So let me tell you how it works in general. So in general, we don't just start with one group, but we start with a huge number of groups. No, maybe I'm exaggerating. We start with a sequence of groups. What is a sequence? It's a twisted Levy sequence. So that means we, for example, could start with GL4. Inside there, we take 2 copies of GL2. Inside there, 4 copies of GL1, and take a twist of it. Twist means that we take subgroups that become isomorphic to this after some field extension for the experts. But if this is new to you, just think of this sequence here. The details of the construction don't really matter. The point is we don't just start with one group, but with a whole sequence of groups. And then we take a point in the building. But now it's getting more difficult. We take not just one real number, but we take a whole sequence of real numbers. And we take a whole sequence of characters. So as Max said, in general, it won't be just one character. No, actually, the input for use construction is a whole sequence of characters. And on top of this, also a depth 0 piece. And then what we do is, out of this, JK-use construction constructs a compact open subgroup and the representation rho K. And as Max indicated, this rho K is much more complicated, not just the character. Because what is this rho K? Or what is the K? The K is glued together out of all these subgroups at the corresponding depths and slightly larger than that. And this rho K is now glued together of all these characters. So all these subgroups restricted to this corresponding depth should act via these characters. And then we also have a depth 0 piece that we need to add in. So this rho K is really highly dimensional. So we glue everything together and make it slightly larger and make it slightly more complicated. But the idea is that we do it in such a way that if we compactly induce this representation, we obtain a super classical representation. And I'm sorry, I can't really explain this, and I have 3 minutes left. There's no way to explain the details of the construction in 3 minutes. I just want to give you an idea that there's just a much more complicated input, but the idea is the same, that we build out of this a rho K, which is just a bit more complicated, takes everything into account, and then we compactly induce like on the previous one. And now if we want to go the other way around, we can start with recovering the first real number by just taking the smallest non-negative real number that has non-trivial fixed vectors if we go to the next filtration subgroup as before. And then, as I indicated before, out of that we get a character. So that's a character of the filtration subgroup of depth R1. Basically the same as, I mean, this is the same argument as the same argument here, because we have in that, now in that setting it will be an R1 because we will have different R's. So this is just the first one. And again, we have this action of an abelian group on a vector space, so we can recover a character. Oops. Go back. So that means that's how we get a character. And this is already, that's what Moy and Passat did. This R1 is called the depth, and this is the unrefined minimal K-type that Moy and Passat defined. But the problem is that this is only part of use data. We need much more. So the secret basically was to just keep going, to define another subgroup, the subgroup G2 that we need, which is roughly speaking the subgroup on which the character phi 1 doesn't tell us any information. And then once we have this, we can restrict our representation to the subgroup and look at the depths for that group, this representation restricted to that subgroup. It's not quite that depth, it's somehow constrained depth, but because what we want is, we want G2 at depth R2 to act via a certain character. At the same time, we want our original group at depth R1 to act via phi 1. So this is the constraint depth. So it's getting much more complicated. Let me not go into the details, but just say the rough idea is we just keep going, construct the next character, find the next group, and then keep going, construct the next step, the next character, and so on until we end up with the last group, and then add the depth 0 piece. And to make all of this work, you have to prove a lot of things in between. You have to prove that all these things exist, that they all satisfy nice properties to go into JK-use construction so that everything works out in the end. So this is the very, very simplified idea of the real proof, but I just wanted to give you a feeling how it works. And in the end, a lot goes into it, like the whole spreadsheets theory, Passat filtration, following along one parameter subgroups around the building, understanding the representations, defining nice properties about the characters, proving that such nice characters exist. So there's much more behind it. I just wanted to give you a feeling and basically show you it's rather explicit. You can actually get it explicit by really reconstructing the input from the output, which is very different from Julie Kim's approach, where she just showed abstractly that things exist. Right, let me stop here. Thank you, and ask for more questions.
Thank you very much. Any questions? So where does the trouble with the small p comes in?
The problem with the small p, so for those two, okay, for number theories, is the tame versus wide extension. So in JK, you can only deal with tori that's split over tame extension. And for the small regions, you need to deal with tori that's split over wide extension.
Okay.
So the idea is basically that people in representation theory usually avoid the wide setting because a lot of things break down. Like the Brecht-Tietz building no longer behaves nice in the wide extension. And there are a lot of problems there. arise from there. So the quick answer is the wide extensions provide that cover.
So where does it stand for you? You think you have a recipe like that extends U and that will cover everything, or?
I'm able to write down some representation that we haven't seen before, and it's work in progress to try to go beyond, try to find everything, but that will be very difficult because already from the work of Bushner and Kutzko, who treated GLN and for generality, you see that things get much more complicated in the wild case. And now you have to combine these two difficulties to not just treat GLN, but treat the whole general reductive groups, which makes it more difficult, and then include the wild case. So there are these two different paths that have been done so far, either the wild case or the general groups, and now combining both is the difficulty.
But the working assumption is that something like a recipe in these lines, along these lines, should exhaust everything.
And that's the hope. Yeah, that's the folklore conjecture that everything arises from compact induction, and I have no reason to believe otherwise. So that's the goal, the hope. Yeah.
Okay, thanks a lot.
I think there was someone raised the hand.
Jessica?
Yeah.
Hi, and I have a question about the regular supercuspidal representations constructed by Fintzen.
Yeah.
What do those representations look like in your picture?
These representations, they would be, let's see if I have a different color, would be all, oops. Well, great, my pen stopped writing. So let me say this instead of write. What I meant to do is circle almost all of the dots. So almost all of the representations in the large region are regular supercuspidal. I mean, almost this, whatever almost means, but most of the representations are regular supercuspidal.
Okay, but there exist representations that are not regular supercuspidal. For example, for P very large.
It's even for P very large. So the idea is, I said that, let's go one slide back. I said that we have as input the depth 0 piece here. The depth 0 piece is a representation of a finite group of Lie type. And so representations of finite groups of Lie type, they were constructed by Deligne and Lustig. And Deligne and Lustig defined some representations that are, I don't know how they called, I think they might have called them even regular. So they defined representations that correspond to Tortori, and they're really, maybe they call it regular character of it. I forget the notation they use. And so Tasha's notion of regular supercuspidal representation are essentially those where the step 0 piece is this nice Deligne-Lustig representation. So it's an RT theta on the nose. So Deligne-Lustig define these RT thetas if you're familiar with it. And the one.
So even for depth 0 supercuspidal representation, the construction of Fintzen is not exhaustive, right?
Correct. Correct.
Okay.
Unless you, I think in GLN all representations might be regular supercuspidal, because I think in that case all the representation of finite groups GLN are. But in general, that's correct. Yeah, and the abstraction for depth 0 to be regular is the same as for higher depth, because it's just the condition on this depth 0 piece being particularly nice. It comes from an RT theta in the nose.
Okay. Thank you.
You're welcome.
Okay, so maybe let's thank Jessica again. And,
I think there was another question, or sorry.
Yeah, I just wanted to ask how you're defining depth. Is that just depth as a G module, like in the usual sense? Or?
Oh no, that's an excellent question. So the depth is actually defined by precisely this condition here. So I said the R in general, for if you start with the representation pi, I said R is the smallest non-negative real number such that the representation has some fixed vector under filtration subgroup of depth R plus, and that's actually the depth. So this here, this is the depth. Okay. So you have the filtration that I indicated on a previous slide, this filtration, for example, the congruence filtration, and you just check how far do you go down in the filtration until you have some vector that's fixed by this filtration subgroup. And that's then the depth. You do this for all points in the building and take the minimum.
Okay.
That's an excellent question.